Okay, and welcome to our session 8 now of Introduction to Machine Learning. We have just one more session after this, which will focus on a very high-level overview of deploying models into production, and we'll use the other half of the time to actually do our exam. Next week, I am out of town, so we will not be meeting at all next week, and we'll do that session 9 the following week. I will drop the exact timeline of that in the Slack channel. But for today, we're going to focus on two things. We're going to focus on neural networks and picking up on the pieces that we left off last time. We'll go through a brief summary of the stuff that we talked about so we can reorient our knowledge and our thoughts to be in that place to finish the neural network content. We left off on activation functions. And then we'll dive into large language models. And this will be similar to the way that we've talked about neural networks, where I'm really focused on exposing you to really particular definitions and terminology so that you can take those and navigate the field. And I'm going to give you two really good resources for further learning by a particular author that I think has done a fantastic job describing that space. So let's talk about neural networks. Let's reorient. We said neural networks are functions. All of the models that we've learned about so far in this class are all functions. They take data and they train weights and biases in order to make a representation of the world. As George Box said, all models are wrong, but some are useful. So they are not human brains, they are not human networks, but they mimic some of the structure, a very gross oversimplification of our human brain and the way that the human brain works in terms of taking input. And then in our models, they're applying a mathematical computation to it and then sending that output downstream to another neuron and working together as kind of a coordinated meshed system. We talked about the structure of a neural network. We defined what neurons are, what nodes are in the network. We described 3 different types of layers. You can have an input layer, which is the numerical representation of the data that we're passing as input to our model. So in our MNIST example of our numbers, our input was an actual numerical value that represented a pixel and how grayscale the image was on a scale of 0 to 255. So it was a numerical value where the combination of all those values represented our image. You can have hidden layers, which is when those nodes, those neurons are passing information to each other and making transformations on that information that was passed to each other in order to find patterns or make decisions to the final output layer. And the output layer is what we're actually trying to predict. Is it a 0 or is it a 1 or is it a 2? Is it a 3? Is it a banana? Is it not a banana? Is it cat? Is it not a cat? Is it a dog or is it a muffin? So these are those are the components of the network. And here we started to take those components and what we're understanding about neural networks and apply it to a really specific example so we can map some utility to those values. So we talked about the MNIST data set, which is this series of over 70,000 grayscale images. There's 0s, 1s, 2s, 3s, 4, 5, 6, 7, 8, and 9s, and they're handwritten values. And you can see all the ones don't look the same. The 2s have some variation in them. These numbers are supposed to represent the different ways that humans might potentially write these numbers. It's a really well curated data set. It's well cared for, and it represents kind of the standard in neural networks in image processing. So it's sort of the hello world of building a neural network to process image data. And it's sometimes in academic papers used as a standard. So if a new architecture or new methodology comes out or a new technique, one might say, hey, it had X amount of lift on the MNIST, image handwritten digits data set. And that's something that people have tracked the performance on over time compared to other methods. And so it can sort of offer a benchmark for comparing different enhancements in the space. We talked about what the MNIST data set actually represents and how we would take something like an image in the MNIST data set and actually represent that as numerical information for these models to process. Because remember, this information has to be put into a numerical value, because at the end of the day, we're taking numbers and multiplying them by other numbers. So we have to have a numerical representation in order to do that. In the case of these grayscale images, a very simple way that you could do that is to have a value from 0 to 255, where 255 represents the darkest colored parts of the image, and 0 represents just white. And anything in between would represent, these grading color values. So you can see the number 3 here represented with those numbers accordingly. So how do we take that image and actually put it into a neural network? We could take this image and break it into 28 by 28 pixels, which 28 times 28 is 784, and 784 pixels would be our input layer. So we would take each of those numerical values that we had on this slide previously, and that would be input into our neural network. Then we have a series of hidden layers. In this case, we have just one, and perhaps it's 64 units long. And we would apply some transformations and then a softmax activation and transform that output into a series of probabilities, 10 different probabilities that all sum to 1. And each probability represents its likelihood of being one of those numbers, where this first node would represent the probability of this number being a 0, the probability of this number being a 1, the probability of this number being a 2. And if this probability was the highest among all the other probabilities, we would then recommend that this is a 2. The neural network would produce an output of 2 associated with this highest probability. We started to look at what is actually encompassed within a neuron, a node of the network, and we've started to uncover that it is simply our in the case of where your activation function is our logit transform from logistic regression, then it is simply a logistic regression formula where we have our y equals mx plus b, or as we've started using our y equals beta sub naught plus beta sub 1 plus beta sub 2 ... beta sub n. And now we're transforming that one more time to a simpler representation where y is equal to w times x plus b. So w is our weights, and b is now our bias. So instead of saying beta sub naught, we now say b. And instead of saying beta sub 1, beta sub 2, beta sub 3, beta sub n, we just say w. And w just represents the vector of our weights. So it includes, in this example, w sub 1, w1, w2, all the way to w sub n. And we would take those weights times the matrix x that we're inputting as our input. So x represents our input now. We just pass, or we just represent it as 1x. But really, when we say x, we're representing this entire thing here. When we say x represents all of this. And then w is our weights. And then b is our bias that gets added to that formula. We take that and we transform that with an activation function. So we're very familiar with the 1 over, I believe it's 1 minus e to the negative z. I have it on here somewhere, and that's the activation function that we're gonna talk about and be familiar with, and then we'll explain a few others as well. But while you're using that activation function, this is just a logistic regression operation in one node. I was seeing if I had, no, we're good. Just had another person join, seeing if I had a question. Okay, so this is describing that concept a little more. Building on that concept, in neural networks, we have more than one neuron, more than one node. And so there will be many logistic regression operations happening at once, many of these weights times biases, and even the output of those feeding into another neuron, and that neuron doing additional transformations on top of that. So this neuron here at the end is actually taking as input the output of these other 3 neurons, and then it's applying its own transformation. So it's doing its own y equals weights times weights times x, w times x plus bias, and converting that to, in applying an activation function and converting that to its output. We talked about the way that neural networks learn, how information is passed through the neural networks in a forward direction called forward propagation. We talked about briefly about activation functions. We're going to dive into that a little more, and how there are transformations applied to the output of the y equals mx plus b of the weights times x plus bias. And we talked about back propagation and how when a neural network makes a prediction, we can compare to what the correct prediction was in supervised learning, and then pass that information backwards through each node and apply transformations to each node so that they can learn how far off they were, and then use something like gradient descent to update the weights towards some direction with using some type of step to figure out how much to update it. So we talked briefly about back propagation at a conceptual level. We didn't dive into the math here about how, hey, we have a y hat that we predicted. We have a cost function, maybe mean squared error. We're taking the square root of y hat minus y. How far off were we in predicting the price of a house? We were off by $20,000. Well, let's tell that to this node. Then this node can transform that information to the right representation to pass it to this node, so that this node can tell how far off it was in its output from getting to that. If it had passed the correct output to this final node, in order to enable it to predict $20,000, what would that have been? So we can take that and we can continue to pass that back through the entire network. So that's back propagation. Gradient descent is the way that we are determining, once we know how far off we were, once we know our loss, how do we actually move in the correct direction, and how do we move the correct amount? So how much do we adjust? How do we adjust our parameters is what gradient descent is helping us understand. We talked about how gradient descent can be complicated at times. We can accidentally fall into local minima and not global minima. We can, and this is where I think we started to leave off here. We have, local spots where we could accidentally fall into this spot, and you can see our steps are getting smaller and smaller, and we don't actually get to this larger point. We can hit saddle points where it actually evens out, and our algorithm doesn't progress any further, and that can cause it to stall. We can hit vanishing or exploding gradients. This one's particularly interesting because our step size, what you need to do to solve this is actually have a smaller step size as you get down here, but our step size was too big. And so what happened is we jumped to this other side, And then when we got right here, the algorithm realized, oh, I thought we were going downhill and now we're going uphill. We're going the wrong direction. So we need to go up this way now. We need to move this way. And so it updates it and it ends up over here because the step size is too big. And then you basically get in this loop. You get in a loop of doing the same thing over and over again where you bounce back and forth. So that's another challenge that needs to be addressed with appropriate step sizing. This is another one where you can actually skip over your minima, and in this case it's a local, but it could be a global. You can imagine that, very steep, and this is the step size is too big here. And having a step size too small can be a problem too, because then your algorithm takes a long time to get to where it should be. So there are challenges and trade-offs to everything. Okay, here's where I believe that we left off, was activation functions. So we're going to continue to pick this up here. Here, I have the formula now for sigmoid. It was not 1, I'm sorry, it was 1 plus e to the negative z. So activation functions, these are what we choose to apply to the output from one of our neurons in our network before we pass that information to the next neuron. So they're important because they enable our neural networks to learn really complex patterns in the data. So really complex representations of our output variables, where things aren't just a very simple XOR. So I have a neural network playground link that represents what that means, complex patterns in data. I'm not quite sure when we get to that. So I think it is in here. If not, remind me at the end of the neural network section and I will pull that up. So there are some common activation functions. One you are very familiar with here is the sigmoid function. So when we have our y equals mx plus b, our y equals our weights times our x input times our weights plus our bias, that's what goes into this z part of the equation up here in the upper right hand corner. And the output of that is this function here that scales from negative infinity to positive infinity on the x-axis. And the output is a value. So it can take anything from negative infinity to positive infinity. And the output is a value between 0 and 1, which is very natural for us because it represents probabilities. It's an easy way for us to interpret the output of a machine or a neural network in terms of probabilities. So the most common application of a sigmoid transformation in a neural network is on your final layer, on your output layer. If you are trying to predict a binary classification problem, you apply a sigmoid transformation. So if you are trying to predict, is this a banana or not a banana, then you would apply a sigmoid transformation to that, and it would give you a 2-class output for your model. There are times when you want more than 2 classes. There are times when you want a multi-class prediction. So our MNIST data set, where we have all these numbers ranging from 0 to 9, and we want to predict, is it 0 or is it 1 or is it 2? And it cannot be both. It's either 1 or it's 2. It's not 1 and 2. In that case, it would be appropriate to use something called a softmax function. So the softmax is used for multi-class classification problems, and it will convert those values. It's a generalization, by the way. It's a generalization of this, of this sigmoid function that allows us to have multiple classes in a way such that all the classes sum to 1. So if you take the probability that this image was a 0 plus the probability that this image was a 2 plus the probability that the image was a 1 all the way down to 9. All those probabilities added together for one image from a prediction standpoint, the output of the prediction, they will all sum to 1. So when you get a prediction from the softmax function, you're not just going to get one value, 0.5. You're going to get a list of 10 values. And there are 10 numbers in that list. And each of them are a probability associated with each of those potential label outcomes. The sum of all of those for every prediction you make will always sum to 1 because that's what softmax does. So this is the softmax activation function. You will see it most commonly used on the output layer for multi-class classification problems. I think I even had that here. So this is a softmax activation layer, softmax activation on our output layer, because we have 10 classes. There's more than 2 classes that we are trying to predict. Okay. I think that's everything I wanted to say on that one. There are many other activation functions. However, there are 2 very commonly talked about other activation functions, and one is tanh and the other is ReLU. So the tanh is similar to sigmoid. It is also an S-curve, if you notice here. However, it outputs the values between -1 and +1. So it's stretched a little larger, and it centers at 0. And instead of centering at 1/2 and centering at 0.5. The other is ReLU, and if you look at ReLU, it's commonly used in hidden layers, and it really only gives a signal after it gets past this point here. So it treats all of these values the same. You know, the output here will always be 0 until you get to this halfway point, and then it starts to give you signal, starts to give you value, and it scales up pretty fast here. So this is ReLU, this is tanh, this is sigmoid. I think you guys have enough familiarity now to sort of explore that domain a little more and really be able to understand when these things are being used. On this slide, I think I was just trying to illustrate that your activation function on, let's see, this is A2. Your activation function here takes the weight times the value, I'm calling it A here, the output from A1. So this activation function here would take the weight from and the value of A1 times the weight and the value of A2 plus the weight and the value of A3 times the bias. I think I was trying to emphasize the actual value times the weight, but I think you guys are pretty set there. Okay, we talked about the sigmoid activation function. Let me see if there is anything else relevant to say here. It's used, I kind of spoke to some of these earlier, so I apologize. It's used to map any input value to a value between 0 and 1. And again, it's suitable for those probability outputs when we're predicting binary classification. So an example here, I remember why I put this for the example. The example here is, should we approve this loan or not? And when you go to apply for a credit card or sometimes a home loan or a car loan, sometimes you put in all of your information and they automatically tell you if you are approved or not. They don't typically tell you if you're automatically denied, but they'll automatically tell you if you're approved. And they might use a model to do that, not necessarily a neural network, but let's think about this in the form of a neural network. We can take applicant salary as x sub 1, the father salary, the spouse salary, and maybe some bias is in our trained model. We trained one of the parameters of bias. We can take these inputs, x sub 1 times our trained weight plus x sub 2 times our trained weight plus x sub 3 times our trained weight. We usually simplify that as just x times w would be the simpler way of writing that. And then, of course, we add, so we sum all those inputs together, we add our bias b, and to that, we pass that to x. So we would add our transformation function, our activation function. It would be 1 over 1 plus e, and x is equal to z here. This little x is z, this formula. Okay. Are we solid on sigmoid activation functions? Good deal. So softmax is the generalization of the sigmoid activation problem for multi-class classification problems. I should have waited to talk about it till I got to this slide, but this will just re-emphasize it. It will convert our raw scores, our raw output, sometimes referred to as logits, into a probability distribution over n classes. So if we have 10 classes, they sum to 1. We have a probability for each of those. This one, for example, we have a classification of 4 probabilities here. You can see 0.91 plus 0.06 plus 0.01 plus 0.2 should, in fact, sum to 1. This was our actual output, though. When we say the raw scores or the logits, these are the values that the model actually output: negative 0.1, 3.8, 1.1. These are harder for us to understand and harder for us to work with from it being intuitive from from that perspective. So applying that transformation, that softmax activation, it doesn't change the value of it doesn't change the order of these numbers, but it makes the numbers more interpretable for us, and it makes it easier for us to look at this 3.8 compared to negative 0.1. It's easier to have confidence in saying, hey, 0.91, wow, it's very confident that it is this value here, this label here. So that's the value of the softmax activation function, the sigmoid activation function, those activation functions that you're applying as transformation on your output layer. Okay, this is for you guys later. We don't need to go through this. I started to talk about it. So logits and log probs. This is a term that will be helpful for you as you navigate through some of the reading on neural networks. Logits are the raw, unnormalized output values from the model. So when we say what were the logits, those are this value here, this output vector, those are our logits. It's just the raw produced output, the y equals mx plus b from the final layer before applying the activation function. So that's our raw logits. They can be used to represent the model's confidence in each class, but they're not yet transformed into probabilities. So log probs are when we actually get the probabilities associated with each thing out of the model. So if you're working with a large language model, for example, and you ask it, you're asking what the next word prediction is, and it gives you a word, there's a probability associated with that word. And there's actually a probability associated with all of the words all of the segments of words in the corpus that the model is working with. And so the log probabilities are helpful to understand and helpful terminology to have as you navigate further. Okay, question for you guys. How many classes are in this problem?
4.
Nice. Yep, we have 4 classes because we have 4 output nodes, so there's going to be a probability associated with each of these. How many features are we inputting into this problem?
5.
Perfect. We've got five nodes here in the beginning, so our input layer is 5, so there's 5 elements of features that we are putting into this. How many parameters are in this network?
3.
So we have parameters are going to be weights and biases. So count the number of weights, count the number of biases, and then add them together.
9 then? Maybe? Or do we count the node itself?
We have 9 plus 4, so 13. So I think you counted weights here.
Just the weights.
Just the weights. So we have this weight associated input 6 for the input to the hidden layer. So we have 1 weight here, 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 1 weight here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So anywhere you see an arrow, that's a weight. And then we have 3 hidden layer biases and 1 output layer. So anywhere you see a node that's not an input node, there is a bias. So there's a bias inside of this yellow node here, here, and here. And there is a bias inside of this blue node here. So in this model, there are 9 plus 4, so there's 13 parameters. I want you guys to remember that when I show you how many parameters are in GPT, in ChatGPT. So we are learning these concepts for a reason. I promised by the end of this, we would get to some concepts around large language models. And one of the things that they put out when they produce new large language models is how many parameters are in this model. That helps you understand the size of it. Because you can see every time we add another node here, if we added another node here, for this particular instance where our input size is 2, we're going to add 1, 2, 3, 4. We're going to add 4 parameters each time we add a node in this architecture. So this will be helpful, I think, as you guys see the number of parameters, which I have later in the large language model section, associated with the GPT models and other models. And that helps give us an understanding for why they're called large language models, because the size of them is fairly astronomical. Okay, so that's important to be able to understand how parameters in a model are formed. There are different types of neural networks, and I wish we had the time to dive into these. If I was you, this is what I would dive into and learn a lot more about, particularly convolutional neural networks, CNNs, which are still very relevant today, and recurrent neural networks, RNNs, which are really the foundation for the way that we build neural networks today, or I'm sorry, the way that we build large language models today. So we have feed-forward neural networks. When we were looking at some of these previous examples, all of the input layer was connected to all of the hidden layer, and every hidden layer was connected to each other, and the information only moved forward. These are the first type of, these are one of the initial forms of neural networks, and they're called feed-forward neural networks, and the information moves from one direction to the other, and they're typically fully connected. Convolutional neural networks are capable of, they're really good in the image processing domain. first of all. So this is an example of a convolutional neural network, and they use convolutional layers to learn spatial hierarchies in these images. So they will compress information in different ways and expand information in different ways in order to pull out particular elements and parts of an image. So these are CNNs, still very relevant and something you could develop internally. You could develop a CNN for your organization to detect images at times. Well, some of these large language models can perform well. It may not make sense from a cost-effective standpoint, from a cost perspective. And it may make a lot more sense to train an internal model, an internal CNN, to do some type of image classification, for example, because it's a lot more cost effective. And you can even use the large language models to teach your CNN how to do that. So you can do some type of transfer learning. Recurrent neural networks is sort of the neural network type of, oh, I just lost, sorry, still recovering mentally. Oh, I hate that I can't remember it, but it's a recursive programming, sorry. It's the neural network equivalent of recursive programming where and it's really well designed for sequential tasks, perhaps like time series or like next word prediction. So you have a sentence with several different words in it. How can you take that information? And there's a pattern, there's a series of operations that are going on there, right? If you have a sentence that says the dog runs fast and you ask your model, here's the word the, can you predict dog? And all it knows is the, then it predicts dog. And then you tell it, yep, you were right or wrong on dog. And then you say, okay, can you predict the next word? And here's the, and here's dog. And here's what you predicted for dog. Here's how correct you were on dog. And now can you predict the next word? And the next word is runs. So it builds on itself. So these recurrent neural networks. And then that just leads us to, deeper architectures and larger architectures. So one piece of information that I think is useful to know, because it can be very different from what we have been talking about when we've been talking about machine learning methodology. We've been talking about train, test, split. We've been talking about training our data. And there is a piece of nomenclature here in neural network training called epochs or epochs and batch size. And in neural network training, typically our data sets are fairly large, because even if we're looking at this image piece of data, sorry, it's way back here, that we were talking about originally, that's a substantial amount of information just for one example. And we have thousands of these examples. And this is a very oversimplified problem where we're trying to just represent one drawing of a number inside of a grayscale image. Now imagine if it was color, and imagine if it had a background, and imagine if there were different ways in which people had written this number. Some people took a picture of it on their iPhone camera, and some people, took a picture of it with their Canon EOS camera, and and some of them are digital. So you can start to introduce more complexities into what an image is and what it represents and what you're trying to pull out of it. And with all of that, it can turn into a lot of information to train your model. And if you just do your traditional train, test, split, and you give your model all of the information and say, go train your weights and biases with this, it can take an astronomically long time. And so what the typical pattern for model training is in neural networks is leveraging something called epochs and batches. So an epoch or an epoch is one complete pass through the entire training set. So on the right side over here, we have a data set maybe of images, and we have 1,000 images. What we're going to do is we're going to break that data set into a series of 100 batches. So we're going to set, batch size of 100. Yeah, 100 batches. We're going to set our batch size equals to 100 here. And you can see that that gives us an iteration. We have 10 iterations over this when we train our model. So when we update our model's weights, when we go through and we do a forward pass, and this training process here, we do initialization, we do a forward pass, we do a loss calculation, then we do back propagation, and we update our weights. We're going to do that on our batch sizes. So we're going to do that in each batch and each, iteration. And then we can define how many times we want the algorithm to go through the entire data set or how many epochs. So these are iterations. Iterations are a subset based on batch size of our entire data set. And an epoch is how many times did you go through your entire data set. And we update the weights on these smaller batch sizes because it's just more computationally efficient to do so, to update on smaller amounts of batch sizes. There was one more thing I wanted to say here. Oh, initialization. When we start this neural network from scratch, we initialize with random weights. So this is just another situation where if you don't set a random seed and you initialize your neural network, I initialize mine, we both train them, we could get very different results just due to the introduction of randomness. So for purposes of reproducibility and repeatability, when you are developing something that you want somebody else to be able to verify and produce the same outputs, typically if you're releasing to production, or if you're working with other team members, if you're doing research, you should set a random seed for these things. When we create the weights and the biases, our y equals mx plus b's, our w's and our b's, initially those are created with random values and prior to us actually training across these batches and epochs. There are a large number of applications for neural networks. CNNs are often used to classify images, used in driving and facial recognition, medical imaging. Natural language processing, or NLP, uses recurrent neural networks, and LSTMs, long short-term memory networks, uses those for text generation, sentiment analysis, speech recognition when you talk into your phone and it's translating things for you as you drive down the road, time series forecasting. There are probably many ways that you interact with neural networks in your everyday life. The advantages of them is that they're very flexible and they can learn complex, here's the link I was talking about. They can learn complex patterns in data, making them, I'll go through these two slides. I think these are my last two. Okay, yeah, these are I'll go through these two slides and then we'll click on that link. They can learn more complex patterns in relationships than our linear models can that we have talked about in the past. And so they're more applicable to learning complex things with large pieces of information and working with very, very large data sets. Sometimes the linear models can overgeneralize things. Every time you have a house, number of bedrooms, you multiply it by 5. And we know that there are edge cases, like when it's in this area and when it's in this one, then it's worth more or less. And the neural networks can capture a lot of those really complex niche relationships. And they're very versatile. They can be applied to a large set of domains. from classification to image processing to natural language processing. Some of the challenges with them are, of course, that they take a very long time. They can take a very long time to train, especially when we say deep ones, it means larger ones, more parameters, so more nodes. They can take training and updating the weights of all of those. You can see how through gradient descent and through back propagation, the more parameters you have to update and train and learn to be correct, the longer amount of time it's going to take. And furthermore, in addition to taking a long time, there's also a larger dependency on larger data sets. So your model may not do well with only a couple thousand examples. You might need thousands and thousands or hundreds of thousands of examples in order for your model to actually get very good at what it's doing. It's very use case dependent on the architecture of your network. That's not necessarily true, but generally speaking, some machine learning models might be able to do well with a couple hundred examples. You might find that challenging when working with neural networks. People typically view them as quote unquote black box because they've been seen as difficult to interpret because there is a lot of chained computation going on in the way that they manipulate the input into various representations. But people are becoming more and more creative every single day with ways that we can leverage tools and technologies to pull out relevant pieces of information from the neural network. It's just the trade-off that we have. It is a more computationally complex piece of machinery. The amount of mathematical formulas in it is much larger, hundreds of thousands, if not millions and up to billions of equations going in there. And so it is harder to understand, but at the end of the day, it is still numbers being multiplied and added and subtracted perhaps together. So I don't love the term black box, if you can tell. It seems an odd line to draw, but they are more sophisticated pieces of machinery, so they can be more difficult to describe, but there are benefits and trade-offs to that. Whereas on the other side, if you're working with a very simple model, it might be easy to describe, but it's going to make a lot of gross generalizations that may not be representative. So the right tool for the right choice is the end. The right tool for the right problem, the right choice for the right problem is the end story here. In addition to training time is, just taking time is one thing, but the computational power is another piece. So some networks that you train actually can't run on CPUs. They're not capable of running on CPUs. It's not enough power for them. You're going to have to switch to GPUs and TPUs. So that can be expensive. That can be costly, and at large levels that may not even be available. So that's just something to consider with that implementation, which is also relevant when you're trying to fine-tune large language models. Okay, let's look at this example I have an actual coding example of that exact problem, the MNIST problem. But before we dive into that, I want to caveat that there are two different sort of competing languages within the space. So back in the day, there were two different, it always seems like there's two competitors, two things that really come to the front, and then eventually one of them becomes a forerunner, but it can take a long time. It can take years. And so, some time ago, it was Python and R, and they both had really, really well-developed packages for data science and machine learning. R was really well known in the academic domain, and Python was a little more leveraged in the enterprise domain because other developers had familiarity with it, and it offered some some object-oriented programming paradigms, etc. And today, really, Python is the only one used, and it's used substantially in the academic domain as well, though I know there are some really great applications and packages in R as well. We are in that same crux, that same moment with neural networks and building neural networks. So as we dive into this code, I think you'll see that this is substantially different than the sklearn code that we have been working with. We have two options. We can build it in PyTorch, or we can build it in TensorFlow. So we cannot build, I wouldn't recommend building your model in your neural network model in sklearn. These are the two packages that have built out functions for building neural networks and really well supported and used heavily. You'll find nice answers on Stack Overflow. So PyTorch is a dynamic computation graph. So it does on-the-fly operations. And what I've heard, just semantically from other individuals, is this is more Pythonic. So there's been a growing, originally TensorFlow was more popular, but PyTorch has been growing in popularity recently because it's more Pythonic, so people are more inclined to use that. We're going to go look at the difference between these two pieces of code with an actual implementation. At the moment, at this point in time, I actually think it's helpful to know a little bit of both, specialize in one. So I would, my opinionated opinion, know a little bit of TensorFlow and PyTorch, be a little familiar with each, specialize in PyTorch. That would be my recommendation. So not to throw another programming language here at you. This is not the right one. I apologize. We're going to reconnect here. If you, while you explore these, oh, did I build this first one in TensorFlow? I did. I built this first one in TensorFlow, so we're going to look at exactly the opposite of what I said, but that's fine. So as you explore these neural networks, I think what you will find is if you don't have a background in object-oriented programming yet, if you're just starting your programming journey and you're starting with scripting and you're starting with Python, it's a great place to start. As you move into neural networks, a object-oriented programming background will help you quite a bit. So learning object-oriented programming for Python, highly recommended. So here we are. This is an example of our MNIST dataset, which contains 28 by 28 grayscale pixels, handwritten images, 60,000 training, 10,000 tests. We're going to import our packages here. We're importing TensorFlow as TF. That's kind of nomenclature. And we're going to import some layers and models here from Keras and toCategorical. And we're going to import some Matplotlib stuff. So we are going to load this data set in. Keras TensorFlow actually has this data set, just like sklearn has some data sets associated with it. So we don't have to manually create that. So we're going to, slightly different syntax you have to get familiar with here. But we're going to load in this data set. Great, we loaded in this data set. And now we're going to pre-process this data set. So what we're doing here is we're just normalizing all of these values. And we're going to convert to categorical our label variables. All right. This is where we build the neural network. So this is why I think it's helpful to have some background in object-oriented programming, because in TensorFlow and in PyTorch, you're going to build your own objects. And in this case, we're just passing a series of parameters to this. But as we get down to, here is the PyTorch implementation, where we're doing the same thing. We're importing We're setting our device to actually use our CPU in this case. And we're creating our training set and our test set. And we are creating our CNN right here. So this is the PyTorch implementation, and we're actually creating a class here, which a class is basically a way of creating a pattern for creating other objects. So you're saying, I want to create a stencil for other people to copy and paste into a particular object. And so my stencil I'm going to create is something called a CNN, and it's going to do some inheritance from this other thing called a module, and a module. And when I first create this, these are things that come along with it. It's going to, it's first going to inherit any parameters from its parent. And then I'm going to set up what the initial structure of this is. And then I'm going to say how it operates. Okay, we're going to jump back up to the top. You don't need to know any of that. None of this is part of our classes or tests or homework that you will do. However, I just think it's helpful to know where you're going. So as you're progressing through your learning, you understand, hey, may not be my objective right now, but as I progress, this is where I want to go, and maybe picking up this additional learning on the way will help me. So when we talk about layers, we have our, all of our hidden layers that we have in those pictures. That is these. So we're defining what these layers are here. We're saying what the input shape was and what the shape, how many nodes are in each of our layers, and what the shape of that is. So are we shrinking our layer? Are we shrinking our information? Are we growing our information? Because just because our image is 28 by 28 pixels, maybe we want to represent that in a smaller form. Maybe we want to represent that in a larger form. So we can compress and expand information through these layers to pull out different pieces of information that are relevant. So we won't go through all of these, but here we have a convolutional two-dimensional network with some max pooling, convolutional two-dimensional network, max pooling, and then we're going to flatten all these layers. And then we're going to do a dense layer. And here I want to point out that we have an activation function associated with each of these. And now you guys know what these activation functions are. ReLU, we talked about the ReLU activation function. And at the end, the very final layer is an output layer. You guys should be able to understand this piece completely now. Is an output layer with 10 neurons. And we know it's 10 because we have 10 classes we're trying to predict, and we did an activation function of a softmax. So understanding these, you need to understand these concepts in order to build this, because an activation function of a sigmoid here, for example, would not accomplish what you're trying to accomplish with this. So this is the information and the knowledge that you're building right now is critical. The next thing we would do, so we define our model here. We've defined it. We've defined what all of the layers are, how, what size we want those to be, what transformations you want. Your natural question might be, hey, how do you decide what all these are? There are like two pieces of information. I would say one is that there's been a lot of research out there, and I would explore the domain, and there's like certain architectures that are known to perform well for certain problems. So you can see that this one is going 32, 64, 64, 64 before you get to your output layer. So there's probably some research to back that. The other pieces, it's a little bit of trial and error. So a little bit of figuring things out in terms of what works. Then we're going to compile our model, where our metric we're using is accuracy. The loss function, the penalty function, that we're using is categorical cross entropy, which you guys will learn about in the metrics course. We focus a lot on cross entropy loss and categorical cross entropy. And the optimizer, which we won't talk about, is chosen here as Atom. Then we can fit our model and we can actually get the history of it. So we can call model.fit. We're going to pass our X train and our Y train, see how many epochs we want to go for, what our batch size is, and our validation split. So you guys should be able to understand this piece of information as well, which is epochs. How many times are we passing through the entire data set? We're passing 5 times through the entire data set, but we're going with a batch size of 64. So whatever the size of our data set is, divided by 64, that's how many batches that we would go through for that. And so you can see for each epoch here, we have epoch 1 out of 5, epoch 2 out of 5, epoch 3 out of 5, 4. I won't rerun this because it takes a minute. And your output that you get from this, we're taking 10% of this data set and putting it into a validation split. So you actually get your accuracy, your loss, your validation accuracy, and your validation loss. So we can actually compare our loss to our validation loss here. And we can see we're getting a little better over time. We're getting closer. We're getting closer validation loss to our actual loss, which is great. And they're getting smaller. We started with a 0.8, which is a higher loss, and we got all the way down to 0.384. So after 5 epochs, we got down to a validation loss of 0.384. After training, we can evaluate this model on our actual validation set, our holdout set. So we can call model.evaluate. We can pass X test, Y test, and get the loss and the accuracy associated with that. We can see our accuracy was about 99%, and our loss was 0.391, which was fairly close to our 0.384. So I would say that our model generalized well. We can visualize the validation training accuracy over time with a plot. So we have the number of epochs. I shouldn't have put half numbers here. That's weird. And so we have 0.94, and we increased over time. And our accuracy exceeded our validation accuracy. Is that true? Accuracy. I didn't look at accuracy. Oh, yeah. So our model became slightly overfit. So we have 8.5, and our validation accuracy was 9.7. 9.7, and this was 9.8. And then if you see by the end, our accuracy is 0.99, but our validation accuracy is actually 0.982. So at this point right here, once we pass beyond that, our model is starting to overfit. So our training set accuracy, when it starts performing much better than our validation set accuracy, our model is no longer generalizing well to our validation set. And that's when we've overfit our model. So that is one really big risk with neural networks, because they can learn so many complicated, it's a double-edged sword, because they can learn so many complicated relationships. Sometimes they learn too many, and they learn niche relationships for your really particular training set that just don't really exist in the real world and aren't what you want it to learn. And so that's why we have a validation set here. So in this case, we would maybe try to dial back and make some adjustments to make it not overfit. This was a great example of overfitting and not generalizing.
Would you like walk it back at all? Would you like say don't do it at the fourth one, use what you got from number 3?
Yeah, there are multiple things that we could do. We could increase the size of our validation split. By the way, we're only using 10% of the data. We could increase that. We could walk this back if we found that every time we went beyond 5 for eBox, it was always overfitting. We just stop it at 4. And if that was good enough. There are other things that we could tune and mess around with within the layers and the transformations that are happening between them. We could make sure that our performance metric was appropriate as well, the categorical cross entropy. And I'm trying to think, we could play with batch size is another piece we can mess with as well. But yeah, we could just dial it back to 4. And that's probably a better spot for it. Okay, here's how we would make predictions. So let's imagine, I'm just going to do this on the test set, but imagine we have new data that comes in and we want to make a prediction on that. So this is our numbers data set. We have a new number we've never seen before and it looks like this. How would you get your model to actually predict that? Well, we would take all that data and we would pass that to model.predict, and that would give us our predictions from the model. And then we can actually visualize what this looks like here. So here is the 1, and the predicted label associated with this is 1. Okay, let's look at any questions on the TensorFlow example so far. All right, we're going to look at PyTorch, and then we will take a break here, and then we'll come back shortly after. We'll take maybe a 10, 15-minute break. So importing PyTorch. So here's all of our Torch libraries that we're going to import. PyTorch is typically referred to as just Torch. You may have to run this line here to check for GPU availability. And then we're going to transform our data set into the right representation for input. We're going to create our training and our test data sets. And again, these data sets exist within the Torch package, so you don't have to actually download anything. Just like sklearn has some toy data sets, this is a toy data set that exists within the package. You just set train to true or false here. When working with PyTorch, it's pretty typical to create something called a data loader. So there's a little bit of a different syntax and paradigm to work with when you're working with PyTorch as opposed to sklearn. We don't create data loaders in sklearn, but when working with PyTorch and neural networks, we do typically create something called a data loader that actually loads a portion of the data set for you. And the reason for that is because when we start working with really, really large data sets, we can't hold them all in memory. We can't hold millions and billions of records in memory all at once in one object. So we need a way to only load a portion of the data into an object and then to work with it, to load a batch of the data into an object. So imagine you work at Facebook or Google or something, and you're working with all of your customer data. You can't store all of that in one object. So you need a data loader to come pull in pieces at a time. So this is the very oversimplified syntax for creating a data loader. So you pass it your data set and your batch size and whether or not you want to shuffle that data set, whether you want to sample with replacement or shuffle, I'm sorry. I misspoke. Shuffle your data set, whether or not you want to change the order in which those values come in. Shuffling your data set is very important, by the way, because when you're training your model, sometimes we're creating. Oh, did I just lose connection? Am I back?
You're back.
Okay, sorry. So imagine we're creating a data set of customer IDs, and we're labeling some information about our customers. We're creating a data set for training. A very natural human thing to do is just to order your customers by ID and start with the first ID, and then you label your second customer. If we just input the data into our neural network like that, what it would do is it would learn a pattern we didn't intend it to, which is probably time they became an employee. Because ID assignment is probably associated with the time that they signed up with us. And so it's going to be trained like it's going to assume that when you give it information that it's always going to be in that order, in that format. And that's not how we want it to perform. We actually want it to generalize outside of that situation and scenario. And so you should shuffle your data. It just means that it changes the order in which these records are presented to the model. So they're not in the same order that they were brought in the training set. Okay, so that's data loaders and why they're important. This is the CNN. We talked about that already. This is just a different representation, a different package for creating it. In this case, we're creating the class. So we're creating the template that we're going to use. We're not actually creating the object yet. But again, we're saying, hey, create a convolutional two-dimensional network here, max pooling, convolutional 2D here, and then a linear transform here to change the size of this, and another linear transform here. And then when you get into the feed forward, this is where we're defining our pooling. And at the very end here, we're doing a ReLU transformation. And we're going to initialize our model. We're going to set the criteria as cross entropy loss. We're also going to use an Atom optimizer for this. And here's where we're actually going to create the function that trains our model. This is very typical in PyTorch. We're going to pass in the model, our train loader, the criterion, the optimizer, and the epochs. And we're going to say model.train. And we're going to say for images in labels training loader. Here are our images and our labels. We're going to grab those. We're going to convert those to the device. We're going to pass that to our GPU. And we're going to set the optimizer. We're going to zero that out, zero out the gradients. We're going to set the outputs equal to the model images. We're going to set our loss. We're going to do backward. We're going to propagate that loss backwards, and we're going to optimize. And then we're going to save what our running loss was over time, and we're going to print out these epochs. Here we're actually calling train model. So this line of code is where we actually do everything that we said above, and we're passing in our parameters. Then we're going to evaluate. I won't go through that. And then we're going to visualize this. Okay, so this is what this looks like. We have 5 epochs again. So we have epoch 1, 2, 3, 4, and 5. We have our loss across each of those epochs. We can see that this loss actually gets lower than the one that we had above. And we have an accuracy of 99.26%. And here's the visual of that was created from that. So I will share this notebook with you guys. It's just a good starting place to get started with that. We are going to take a break. Let's come back at 7:40. It'll give us 33 minutes, or 33, I'm sorry, not 33 minutes. That'll give us 13 minutes. All right, we'll see you guys then. Okay. And we are back to talk about the topic that we've spent the entire 4 weeks building to, which is large language models. So everything that you guys have learned, from linear regression to logistic regression to understanding classification models and regression models, all the way up to neural networks, comes into play here in large language models. I apologize if there's some background noise. I have an upset kid in the background that I'm sure my babysitter will be coming to take care of shortly. So large language models are the neural networks. One moment. Okay. The large language models are neural networks, essentially, but they are very, very, very large neural networks. They have billions, or in some cases, even trillions of parameters, and they're trained on extremely vast amounts of data. And they're really able to perform a large set of natural language processing tasks. So when we're thinking about training of large language models, imagine all of the data on the entire internet put into a model. That is the type of breadth of information that we're talking about when it comes to training these large language models. And the purpose behind these is to really create a model that is designed to understand the pattern of human language better and to be able to generate human-like responses in our plain language, in plain English language, or whatever the language is that you are interacting with this model from. And to do that at scale. So the English language is very complex, and you can think of a large language model as, instead of learning the English language by studying all the rules of grammar and learning what adjectives are and verbs and nouns and pronouns and learning all the parts of speech and the ways that those parts of speech interact with each other, what if you could learn Spanish that way. You could learn all the elements of Spanish and all of the grammatical representations of that. Or you could just go live in a Spanish-speaking country for 5 years, and you could learn Spanish that way. And this is sort of the way in which large language models learn. Instead of learning all the hard set in stone rules, we just give them tons and tons of examples of what language is like, what it is like when we write language on the internet, what it is like when we speak language, when we respond to questions. We give them many, many examples by just crawling the internet for those. And over time, these large language models learn how to represent language in that same and similar way. So I'm going to start to, how familiar are you guys with large language models, by the way? Any background or information?
I've done enough to be dangerous.
Nice. That's perfect. So this may be too high level for you, or it may be useful, or it may not. At the least, I'm going to start to plug in the pieces that we've learned, such as the parameters, and I'm going to speak to a few other pieces of relevant information when it comes to large language models, like tokens, that'll help you to understand and parse more about them. So there are many language models that exist today. Everybody talks about ChatGPT is the one you kind of hear about. It's very predominant in the social media space. But really, there are a wealth of models, and you can find even more models on a platform called Hugging Face. Hugging Face has a series of developed models that you can pull from and work with. But here, if we look to these old release dates, sometime between November 2022 to February 2023, so very outdated. There are many new models today. Some things that you might have heard about in that time would be ChatGPT or just GPT are the models that they implement. You might have heard of something called Gemini. You might have heard of Claude, Minstrel, Llama. Llama is what's used by Meta and developed by Facebook. So these are all large language models, or LLMs. And here's a couple of different release dates, and these are the actual models. So GPT-4o, which is actually a multimodal model, which can actually process images in addition to text. Gemini 1.5 Pro, Llama 3. And there's maybe some prices and speed and quality index and key features here. But the thing that I want you to take away from this slide, which I'm sure you're already aware, is that there is not necessarily one large language model. There are many large language models that exist, and they are evolving every day to have different areas and domains of speciality and to be better at performing certain tasks. And we're continuing to evolve and mature them. So staying up to date with this can help you understand for your use case what's the best model to use and which things are performing the best in that domain or that area. The most commonly talked about one from a media perspective is just ChatGPT. So here I want to differentiate something for you because you are now a technical expert. And so now you know you should know the difference between GPT versus ChatGPT. So ChatGPT is our chat interface that we work with. So it's a GPT-based chatbot, and you can ask questions and receive answers back. It's a question-answer format in human readable language. Now, what it uses to do that under the hood is GPT. And there are actually a series of GPT models that you can select to do that for you. You can select, I think their free version today is GPT-3. Somebody correct me if I'm wrong. But you can pay for GPT-4, 4o. There's even smaller models that you can use. And they even have another type of GPT model that's trained to give you very in-depth answers for more computationally intensive questions. And so there, even within ChatGPT, there are many large language models. Some of them are free because they're older, and some of them are more sophisticated, and they come out with new ones very, very frequently. So the developer for this, and again, you are a expert in the field now, so you should know that the developer for this is OpenAI. OpenAI is the company that develops GPT and ChatGPT. ChatGPT is a chat interface that uses a series of GPT models. And GPT models are large language models created by OpenAI. This is just to emphasize that this has been a very long journey, and that GPT models have been starting their release since June of 2018. And one way of looking at the difference between these models is looking at these model parameters. I promised that we would look at these. 110 million parameters in GPT that came out in 2018. 110 million parameters. Remember that neural network model that we were looking through, and we counted the parameters, and even for a very small model, there was 13 parameters. 110 million. That's almost too much for us to even be able to imagine. And it's hard to believe that in GPT-2, that jumped to 1.5 billion. So very substantial jump in the number of parameters, essentially the size of the model that they built for this. We can, fast forward through all these improvements until we get to GPT-4, which is very performant in performing across multiple languages, and up to 1 trillion parameters now in GPT-4. So you can see that now you guys have the capability to really understand what the parameters are, what that means. That's all the weights and the biases that are encompassed within that model. So it's essentially the size of that model. Again, this was just to re-emphasize the size piece. I probably didn't need both of those. And this this is to emphasize that with great power, with great capability, comes a substantial requirement on investment to build these things. So why doesn't everybody just build a large language model? Why doesn't every business out there, why is everybody leveraging OpenAI? That's a good question to ask. Why is everybody saying, I want to use OpenAI instead of building their own large language model? Because the internet information is fairly widely available. Well, the answer is it's extremely expensive to build models that are that size and performant at that scale. GPT-3 alone likely costs between $4 and $12 million just to train. And GPT-4 was likely substantially higher than that because it's such the larger number of parameters, the greater size. So the requirement on the computational cost. So some ways of trying to map some of these attributes of the model into other similar domains that might help us wrap our head around this is when we think about training size, when we think about number of tokens, what's the size of the input that we put into the model to train? How many books did we give it to train on? This would be equal to 650 kilometers of a long line of library shelves, where each shelf is 100 books per shelf and 2 shelves per meter here. So that's a substantial number of library shelves. Compute size, how long would it take to compute? Well, if we just ran on some mid-sized laptop, it might take 7 million years for us to equal the computational power that it takes to train GPT-4 estimate. This is just helping us wrap our head around it. When we think about model size, 1.8 trillion parameters, we can imagine if we took all those parameters, we know each of those parameters just represents a number, they're just weights and biases. What if we took each of those and put it in an Excel sheet? We would have 30,000 football fields size worth of an Excel sheet. That's how big our Excel sheet would be, which is kind of mind-boggling to think about. So there is a substantial amount of information in these models, and it takes a lot of data, a lot of time, a lot of money to train all of these. So a lot of times when we're implementing these, other industries want to leverage GPT and their pre-trained models for our own implementation, so that we can pay a small subscription or a small call or service fee to leverage that model without having to invest all the money into this infrastructure ourselves. It didn't start there, though. We didn't necessarily just start with GPT. There were things before GPT, and sometimes it's useful to start to understand the contributions that Ngram models made, that recurrent neural networks made. If there is one thing that I would recommend, it's understanding the transformer architecture and the BERT model from 2018, which I'll give you guys some links for that. It was kind of a pivotal marker in the field. Before we can understand some of that, I'd like us to build a little bit of terminology to navigate through the language domain. This is not a class on natural language processing, but if you were to explore natural language processing, these are some terminologies that you would see and would serve you well. So here's some nomenclature. The first piece we're going to talk about are tokens. So in the context of natural language processing, when we have a sentence, we can break that into something called tokens. So we have this sentence, we love NLP. Applying tokenization is breaking that into its individual parts, such as we and love and NLP and exclamation point. So we've tokenized this sentence into 4 tokens. Tokens, in this example, we broke this down into words, but they don't have to be broken down into words. They can be broken down into subwords. They can even be broken down into characters. So here is an example of this is tokenizing. If this is the input, we can break that word down into character level tokens, where each of these is 1 token, or word level tokens. This is tokenizing period, or subword level tokens. This is tokenizing period. So the English language is made up of a lot of words that end in like ing or er or ey, and it may not make sense to create our dictionary that represents all of our words as representing every single word in the human language. Because if we represented every single word in the human language, we'd probably get to trillions of words. And that's very computationally expensive when we're asking these large language models to predict what is the next word. Because what they're really doing is what is the next token. And they're saying, what is the next token given all of these potential tokens? And all of these potential tokens is we're restricting that to our set of potential words that they could output. And if we said, hey, your set of potential words could be all of the English language, that's a really large set. We want to minimize that. So often we use something called subword level tokenizing is usually what's employed, so that we can build other words with subsets of words. So if we want to do the word believable here, unbelievable, if unbelievable is the word, we can build that with un and believable. We can build those 2 things together. So oftentimes we do not predefine this tokenizing. We can use pre-trained. There are experts out there who have spent a lot of time defining how to tokenize these words in the most appropriate and useful and meaningful ways, so we can leverage a lot of those. So how does are tokens used in large language models? What does this have to do with large language models? Well, when you provide that text to GPT, it first breaks that text into tokens. So it breaks it into these individual units and pieces. And if you actually look at some of the differences, comparison and contrast of these various models, you'll see that they have something called a token limit. A limit on the number of tokens that you can put into a model. And it used to be really small. And now we're up to 2,048 tokens. So have you ever been working in ChatGPT and it gives you a response and then it cuts off at the end, and you wondered why it was giving you a really, really, really long response and then it just stopped? Midway through your response, you probably hit your token limit. So you probably hit 2,048 tokens, which it can't handle any more than that. So for that version of GPT. So now you understand what a token is, and you understand that it's not necessarily a word, because we can see down here, this example of the tokenization. This tool allows you to visualize the token, and then S is a separate token from tokens, even though it's the tokens of space a text prompt, and you can see that ver and text were broken apart, PA and LM were broken apart, count E and D were broken apart into separate tokens. So if we look at the word GitHub, G-I-T, and hub were broken apart into separate tokens. So token doesn't necessarily represent one word. Okay. I'm realizing that I'm going to say one more thing on here because it becomes even more apparent later, but I probably should have connected this dot sooner. We talked about for images. No, I'm going to keep going. That seems an unusual point to break it in. We'll just keep going with the flow of the slides. It does come up later. So the relevancy of these tokens is breaking them allows us to process text more efficiently. Like I said, we're not predicting over the entire English language. We're just doing the set of tokens for what we're building towards our embedding. Context window. Models have different context windows, different number of tokens that they can allow within a single model call, within a single model response. And that includes both input and output tokens. And it can also allow us to handle more complex words, which may occur more rarely within our language. We can have a better representation for those by breaking them down into those individual units and pieces. Okay, how are we feeling about tokens? Good. So tokens are how we represent units of words. Now, we can sometimes group those units of words into things called grams. So we can group them into n-grams. So we can group tokens together. Now, I just want to be clear that as I go through examples, I am often going to use words to represent a token. So I'm often going to say this is a sentence, and these are unigrams. This is a sentence, but you just have to know and connect in the back of your mind that these tokens don't necessarily have to be words. They could be subword tokens, and a unigram would just represent those one subword tokens, not necessarily one sentence. Okay, wanted to be clear about that. So n-grams represent continuous sequences. So this is an n-gram where we're saying we're representing tokens at one token level. This is a bigram where we're going to represent two tokens combined together, or two words combined together, or two sentences combined together. So this is one of the bigrams, is the second bigram, and a sentence is the third bigram. This is a, and a sentence. Trigram would be this is a and a sentence. This is a and is a sentence is a trigram. These are very important for understanding what n-grams, bigrams, and trigrams are, because when we start to understand how to evaluate large language models, when we look at something like the GLUE score, the BLUE score, it is based off of n-grams, n-gram level evaluation of large language models. So these are important concepts to know and understand, because as we talk about evaluation metrics, I didn't tag on BLUE and GLUE score here. We can talk about it briefly if we have time at the end. I don't think we will, but if we do, we can talk about that. But we're definitely going to tag it on to the end of the metrics eval course in terms of how do you actually evaluate these large language models? How do you know how well they are doing for your particular task? It's an evolving question. Just to delineate this a little more clearly, unigram, bigram, trigram, if you generalize that, you might just call it an n-gram. You could have, four words together. You could have 5 words together. You could have 10 words, a 10-gram, a 5-gram. So n-gram is typically how we refer to that, and whatever your value of n is how many grams. So in this sentence, is in consciousness studies, the consciousness studies are fundamental. We have in consciousness, everything is its own, token here. And everything is its own gram. And notice that we only count consciousness once here. And here we are grouping them into elements of two. So in consciousness, consciousness studies the consciousness, studies R and R fundamental. And here we have our trigrams where we're representing those as pieces of 3 words. So these would be all of our potential bag of words that we would be pulling from. I forgot to do that slide, so I apologize. We're going to skip that. And I do have, you know what? Sorry about that. I did not. That was not supposed to say blue score. I had a typo there. Next word, prediction. I did not skip this slide. So originally, where this started, before we got to ChatGPT and GPT-4 as it is today, the problem that was trying to be solved in the field was, how do we predict what the next word is going to be? Have you ever been typing on your phone and your phone pops up, I had such a, and then it's recommending 3 options for you for your next word prediction. I had a great time, I had a lovely. This is what it thinks is likely going to be your next word prediction. So this is where large language models really started. It's a very foundational piece of large language models. And really in the way that they generate output today is just a chained continuation of that next word prediction. So let me predict the next word, and then that's how they actually generate that output for you. So very important. If you remember back in the day, these weren't very good. They had a lot of problems, and you could actually hit next word on them. You could keep hitting. It was sort of a game, right? Where you could keep hitting the next word that it would predict and always hitting that middle word and see what it would predict. And it was usually some really funky sentence, right? So clearly there's some new technology that we came out with between next word prediction and just making the next word prediction given the text that you have and where we are today. So we're gonna at a super high level look at some of those things. I really goofed up some of these slides. I'm so sorry, guys. Okay, that was more about n-grams. Oh, no, this is correct. N-gram models were so when we talk about n-grams, now that we just talked about n-grams, it's the appropriate time to talk about n-gram models. There were three main implementations trying to create this next word prediction mechanism. The n-gram models was the most naive and kind of first attempt at this model. And they weren't very good because they were really limited to that context window, so they could only see a really fixed preceding of number of words. And so they would really struggle to capture long run-on dependencies, long-range dependencies. And that's why when you would keep hitting that next word button in your phone, it didn't work very well, because it probably wasn't looking back at the very, very beginning of your sentence. It was only looking back 3 or 4 words before and then making a next word prediction. And that made a really poor actual sentence creation model. It wasn't designed to create a sentence. It was designed to predict the next word given the first 3 words, which it was probably pretty good at, but that really wasn't in the context and the understanding and everything else that's going on in the sentence. So the next evolution was recurrent neural networks, RNNs, which we know a little bit about now, but not very much, and LSTMs, long short-term memory. So we thought, well, part of this problem is that these models remember too much information. And what if we can kind of help them forget information over time? So as the human brain, we forget things over time. We don't remember our childhood so well. but we remember what happened to us like very early this morning, or what happened to us yesterday or a week ago. So this is the idea of a long short-term memory. So sort of building in that idea of forgetting things over time as patterns and things change. So not putting as much emphasis on the older pieces of information as you are on the newer pieces of information. And so as you're working with Google here, and it's predicting potentially the next thing that you're trying to search in your search domain, Google's probably a lot better at that now than your phone was, for example, because they're leveraging the recurrent neural networks and long short-term memory mechanisms within the neural networks. But the really big transformation in the field was when transformer models, and built on all of those things before. These things build on each other. The really big transformation was when transformer models came into the picture and revolutionized our next word prediction mechanism by using something called self-attention. And this self-attention mechanism was a really, really substantial finding for the field and is still very relevant today. And what it helps the model do is figure out, when it's looking at a particular word, what are the other words in the sentence that are most important to be focusing on for that given word. So for example, let me see if I can come up with an example on the fly. Sally likes playing outside, comma, she jumped over the bridge. Oh, that's terrible. I was imagining a very small bridge. She jumped into the pond. Okay, she's gonna go swimming or fishing or something. So when you're looking at the word she, what are the most important words to be paying attention to in the sentence? Well, Sally is probably a pretty important one for us to understand that she refers to Sally. And we do this very naturally as humans. But if we're working with a model that only looks back the last 3 or 4 words, you might not get back far enough to actually get to the word Sally with our traditional next word prediction mechanism, right? So we need something more sophisticated. We also can't just look back at the last million words, because there's a lot of words in there that might not be relevant to what we're trying to predict, to the word she. And so how do we figure out which words preceding the word she are relevant to the word she? So when we're trying to predict she what words are most relevant to that? Sally might be very relevant to that. It may not be the best example, but there are lots of very, very well curated examples out there. And I have a great resource for you guys for self-attention, very well done and frequently spoken about author that wrote a good document for understanding that. And it's accompanied by videos, so multiple modalities of learning. Okay, so let's look a little more at this. So here it is. Here's the much awaited. The page here is called the Illustrated Transformer, and it's by this, I have it open here, and it's by this author here. And the way that they explain a transformer is a really, really good example here, where they're taking something that is in a different language and explaining the architecture of a transformer as taking that other language and translating it to another one. So we're taking Spanish and we're translating this to English. The transformer is taking as input the Spanish words and translating them into English words. And this is what the transformer is doing in this architecture. So this is the illustrated transformer. It's accompanied by a video here. I do think it's very well written, well done, and I would encourage you guys read this. And it really breaks down at a very detailed level how a transformer works. And this is absolutely crucial and critical to the domain of of large language models. So originally in the first paper that came out, which I'll link in our Slack channel around this in the BERT paper, it's encoder decoder architecture, which later we termed as transformer architecture. And the way that this encoder decoder architecture works at an extremely high level, again, it's described much better in this paper, is it takes input and we pass it to this encoder. And what the encoder does is it creates a numerical representation for that information, and it compresses it down to a numerical vector that represents the most important pieces of that information for us. So there's an architecture, a neural network attention mechanism in here, and there's a feed-forward neural network in here that compresses this down into something called a latent representation. And that's the numerical vectorized representation of this input information. And this encoder architecture becomes very, very important in large language models in the future. Then there's something called a decoder architecture, which takes that compressed information, and then it's sort of like having the key to an encrypted piece of information. It takes that compressed information and it decodes it into whatever it's trained to decode it into. So in this case, it decodes that compressed information into English. So wow, how amazing is this? That we can take a foreign language, represent that into a numerical vector that can be decoded into a totally different language with different grammatical structure, with different words that represent different things. English and Spanish do not at all have the same grammatical structure or way of describing adjectives to things. And so the fact that we can take a numerical vector that represents both the English words and the English sentence and the Spanish sentence is pretty amazing. That's super, super powerful. So this encoder decoder architecture is a really big deal. I think I actually already went through this in depth, but these encoders are made up of two components here. We have a self-attention and a feed-forward. And this decoder, if we kind of unmask what's inside of that decoder, we have the self-attention, encoder, decoder, attention, and then a feed-forward neural network as well that translates that information. Here is a better representation pulled from that same website, that same article on attention. So this is the animal didn't cross the street because it was what? When we're looking at it, what is it? Is it the street? Is it cross? Is it, what words should we be paying attention to? And here we see highlighted in orange, it's the animal. So attention is a mechanism that allows us to understand what parts of the words before it and the words after it. Notice that is also a big difference compared to our just next word prediction that we were doing when we were originally on the cell phone. We couldn't see the words after it. This is looking at the words before it and the words after it. Which ones are most important to pay attention to? When you go to actually look at the architecture for these things, you'll probably get something like this. So this it might be a representation of the transformer architecture or the encoder decoder architecture, where we have some input sequence here. This is our input sequence. And these are cast to embeddings, which I think I talk about embeddings. Yes, I do, in 4 slides. So we talk about what embeddings are. So I realized after that there were a few more pieces of terminology to throw at you guys. These words are cast into embedding representations, and then these embedding representations are put into our encoder architecture here. And then this encoder architecture outputs some latent vector representation, some encoded vector representation. That's a numerical representation of the important pieces of this that can then also be translated by the key. And the key is our decoder architecture here. So you might see this represented something like this, and then it produces these output embeddings. And there's a softmax transformation applied to these output embeddings that creates a probability associated with each of these. And those are called the log probs. And now you guys know what those are, the log probabilities associated with each of these. There are also logits you can actually get associated with each of these, which is also just the numerical non-transformed that wasn't applied to the softmax function here, probability for the output. So now you guys know what softmax is, and you know these output probabilities. You know log probs, and you know logits. So I think you guys know a lot more about these large language models than the average person. These are made up of many neural networks. So it's not one neural network, I think, is the piece that I'm trying to work towards here. Throughout this class, we started with linear regression, and we moved to logistic regression. And we learned that when we build a neural network is made up of many logistic regressions if sigmoid is your activation function. And then we're learning that, okay, large language models are made up of many neural networks. And when you work with applications such as GPT and other things, they're probably actually made up of many large language models as well. So another really great paper, web page to read, same author here. So similar writing style and explanation here. If there's one piece I would recommend that you explore and understand, it's BERT. So BERT was released in 2018, 2017, 2018, somewhere along those lines. And this made a really revolutionary difference in large language models. It made a pretty substantial step, and they proposed two different ways of using this large language model. One is a semi-supervised training approach, which is still leveraged today. And this is, hey, we have all of this information on something called Wikipedia. Why don't we just, and it represents how a model, it represents all the text that a human writes today. So instead of having a human go and curate a manual training data set on, I said this, and then this was the response. Let's just use Wikipedia, and let's look at, let's give the model 1 and ask it to predict the next word. And then let's give the model 1 of and ask it to predict the next word. Then let's give it 1 of the and ask it to predict the next word. So if you think about it, we already have a training set called all of the internet, all of Wikipedia, where we can just hide the next word and then give it the next word. And then after it has that word, we can release that to the model, and then we can ask it to predict the next word. So it's a semi-supervised training step, because we're not creating a curated training data set for it. We're just leveraging the already pre-written words and text that exist on Wikipedia. And then they offered a second way of using this model, a second way of using the BERT model, which was, hey, you can actually use this language model for classification. So you can use the BERT model and attach a classifier to it and tell it, hey, given this sentence, is it spam or is it not spam? So this is a pretty substantial move in the field of language modeling and the actual usability of these language models to perform tasks for us, to tell us information that exists within that text. So this very important paper would recommend going through this website. He also has a video that accompanies this. Well done. So the transformers, very important, introduced that self-attention mechanism, and it allowed us to handle those long-range dependencies with applicability without just saying, look at everything. It allows us to really focus and hone in and make things more scalable and more efficient for parallel processing. Okay, I already talked about that piece. Here's the belated embeddings. So forgive me here. This is it's probably the right place for it because there was so much information before. I didn't want to throw too much at you guys. But remember how in images we talked about, well, machines can't actually take in things that aren't represented numerically. At the end of the day, you guys know we're just multiplying and adding things together. And we can't actually do that to images. Well, we can't do that to words either. We can't multiply cat. We can't multiply kitten. We have to have a numerical representation for that word. The word has to be represented as a number. A very easy way to do that, for example, I should have had a precursor slide so you guys couldn't even see this. But a very easy way to do that, for example, let's just take all the words in the human language. Let's start with the first word we see and label it 1, the second word we see and let's label it 2, the third word we see and let's label it 3, and we can go down that list. Now that might not create a lot of meaning in those words. When we compare one word to another word, if we just randomly label them, there may not be a lot of meaning created in our word labeling. So there are a lot of professionals that have spent a lot of time in the natural language processing in the NLP space and created something called word embeddings. And word embeddings map a word to values. And so, for example, in this very demonstrating example, we have the word cat, and maybe this first vector, this first value, this not first vector, this first position of this vector, this is a vector, by the way, 0.6, 0.9, 0.1, 0.4, 0.7, 0.3, 0.2, that's a vector because we can plot that in space. So for this cat vector, maybe this first value in the vector represents living being. Maybe a cat is more living than a kitten for some reason, and dogs are more living than cats for some reason. Houses, perhaps the smaller values are more living because houses are not very living at all. So perhaps this represents feline, perhaps this represents human, gender, royalty, verb, plural. In reality, we typically can't apply such labels to what the numbers are in our word embedding. They're not really quite as interpretable as we're trying to make them be in this example, but we're just trying to give a piece of understanding for how these might be used. The point is, when you put a word or a token, for example, now that we know what tokens are, into a large language model, what it's actually doing is it's converting that to an embedding so that it can understand that. And by understand that, it means it can take that embedding value and pass it through its neural network. Because at the end of the day, these are what are being multiplied inside of the neural network, are these numerical values. So in this picture, you guys know all about dimensionality reduction now. We can actually apply dimensionality reduction to this 7-dimensional vector, and we can reduce it down to 2 dimensions. We can reduce it to an x dimension and a y dimension. And maybe if we reduce it down to an x dimension and a y dimension, we can actually plot it. And we can see that houses is very far away, and cat is pretty close to kitten, and dog is close to cat and kitten, but it's still way over here. You can do the same thing. One of the most famous examples of this in the NLP space is it may be fairly gendered example, so forgive me, it's just a common example. I didn't come up with it. It is man, woman, king, queen. And so we can do the same thing where we have this seven piece vector, and we can do dimensionality reduction on that to bring it from 7 dimensions down to 2 dimensions, and an X dimension and a Y dimension. And we can plot that. And we can see that king is just as far away from man as queen is from woman. And there's some argument numerically that you can make that king minus queen is equal to woman, or something to that effect. So all this is to say, when we're actually putting these words, these tokens into neural networks, they're actually represented as embeddings. And oh, here we are. Sorry, I was going more into embeddings. I've a consistent pattern today of talking through the points I already want to talk to before I get to the next slide. So king and queen have spatial similarities because they're related concepts, as you can see. Man and woman are also spatially related to each other, and the difference between king and queen is similar to the difference between man and woman because of the semantic gender relationship there. Okay. I hope this also lets you know that large language models and embeddings are just trained on the historical data that we've put out there on the internet. And so if changes occur in society, we just have to be aware that what's been happening for the last 100 or years or so, whatever the length of information is that we're putting onto the internet, the models are pretty susceptible to over-representation of information. You guys know about class imbalance. You know how that impacts models. So they're not as adaptable as we are as humans to new and present information. So there can be a lot of bias and unintended behavior when learning purely off of data and historical precedents. Okay, the one more piece I think is, I say one more and then I have like 10 more slides. So not one more piece, another piece of information. Now that you understand the embeddings and that embeddings are numerical information, we can start to represent those as vectors. And as you get to implementing these large language models and information that you're passing back and forth to them, you might even stand up something called a vector database or a vector data store. And what this is storing is your information in vector representation. So we created those embeddings that were numerical representations. And in this case, we're saying goose is represented by 3 numbers, 2, 0, and 4 for this very simplistic example. And what's very powerful about embeddings is we can now calculate the distance from one embedding to another. So we can see visually that helicopter is closer to drone than helicopter is to rocket. And the way that we can calculate that is with something called cosine similarity. I'm pretty sure this is on the next slide. Yeah. Okay, I will not jump ahead of myself this time. The way we can calculate that is with cosine similarity, which is the cosine between these two vectors, if you remember back to high school geometry. I will see if there's anything else to say on this slide before jumping to the next one. Before I continue, are there any questions so far? We've been working through a lot of concepts. Okay, perfect. So I did say that there were some, experts in the field that have already created really good word embeddings. You don't need to go out and create your own. You, of course, are empowered to do that. But a really good place to start is with Word2Vec or GloVe embeddings, to very well-developed natural language processing toolkit word embeddings that you can use. So putting those out for you. Okay, here's the cosine similarity thing. And it's got a slightly better picture here to represent what I was trying to explain. So we have two items, item 1 and item 2, and we want to see how similar they are to each other. How do we do that when we have many, many values associated with them? Our vector for our word cat is like 7 dimensions long. Well, you can actually use cosine similarity, and this is very substantially used today. So this is a very relevant metric that can be used to say, this is how close item 1 is to item 2. Theoretically, you can use cosine similarity to determine the similarity of the numbers in the MNIST data set as well. So we had all of those numbers in that represented the drawing of letter 1. If we just stacked all those values next to each other, one after another, that essentially is a vector. We can represent that as a vector. You can compare that labeled 1 to a different input of a number that we don't know the label of. We can calculate the cosine similarity from the labeled value of 1 to that unknown input, and from the labeled value of 2 and 3 and 4 and 5, and we can see which one it is most similar to from a cosine distance perspective. So that is one way you could develop a good baseline model for the MNIST data set, is just develop a cosine similarity metric before even building your large language model, or I'm sorry, your neural network. And then once you built your neural network, you could say, hey, I have this much lift above cosine similarity for my MNIST data set. Where is the field going, I think, are some of the pieces that I'm going to get to here. So there's sort of a hodgepodge of things here for you. One really revolutionary change that came out in the last year or so is multimodal models. So LLMs are now LMMs now. So large language models are now large multimodal models, LMMs, and they're machine learning models that can process multiple modalities of data. So we've talked about how we can take textual information and how we can put that into a neural network, how we can represent that numerically into a neural network. And now we've talked about how we can take textual information and represent that numerically in a neural network. You can, of course, do the same thing with voice. We didn't talk about that, but you can use your imagination. We can represent that numerically in a neural network. And then we can actually create these latent vector representations across all of these modalities. And we can put that into our large language model and use that as input and as training. And then we can do a lot more complicated things with it. So if you guys have noticed, if you use ChatGPT or anything equivalent, and maybe about a year ago, you weren't able to put images in there. You weren't able to drag and drop images in there. You could only put text in, but now you can put images in. That's because it is now a multimodal model. It's capable of taking image as an input and producing text as an output. And that is how multimodal models are able to do that. They're trained over text and audio and multiple modalities of information. If you looked at ChatGPT 2, they're releasing an audio piece of that to come soon as well. So they are training, continually enhancing and training their models. Multimodal models are definitely making a really, really big impact right now in terms of being able to parse and pull information out of text and documents. So for example, what can you do now? I believe multi-modal came with ChatGPT 4.0, I believe. You can ask questions now, like what is in this picture? Well, it looks like a duck. Well, that's not a duck, then what is it? You can see it has context here because it's remembering the picture and it's remembering what you had said previously about a duck, and then it's changing its mind. Well, it looks more like a bunny. And then why? And then it actually tells you, well, it has bunny ears. So this is a pretty big, this is pretty revolutionary. This is a way of interacting with neural networks in ways that we haven't been able to do, and in large language models in ways that we've been able to leverage before. We're not very many years away from the really bad chatbots that were implemented by many organizations, which weren't fun for us to parse through. This one I think is particularly interesting as well, where you can pass an image of a clock and actually ask, what time is it on the clock, which is very natural for us to do as humans. It's very easy for us to look at that clock and say what time it is. Now, some of these larger models can actually have the capability to do that, to solve problems, of course, here, pictorial problems, to answer mathematical questions that are represented pictorially, etc. So that is multimodal models. Another piece for you to just be aware of and to explore, a natural question you might have is, great, how do I actually use this? Like, how do I take GPT for my life and use it in my work at my enterprise? How do I implement this for my problems I'm trying to solve? Something to explore and to learn more about are the processes of transfer learning and fine-tuning. So the large language models are great off the shelf, but they are not tuned for your use case. They are not curated to perform really, really well in your situation, in your context. But what's fantastic about them is they are something called pre-trained, meaning they've already got those weights tuned. The weights are not randomized. So now you guys have all the context to understand what weights and biases are. Those weights are not randomized. They are trained. You can take that model off the shelf and continue to train those weights. So you can further train those weights, and you know that you're not starting from random now. So it's going to take a lot less time. It's going to be a lot faster. So it's like getting a really good starting point. So you have a really good starting point. You can take those pre-trained models and weights, and you can give it your data set, and you can continue to train those models and weights to get a little closer to find, that global minimum for your data set. So you can get it to specialize in a very particular field and area here. Now there is a trade-off. As you guys have learned, there's all kinds of trade-offs in machine learning and data science. We're always giving something up for another thing. And as you fine-tune a large language model to be really, really good at a specific task, you give up generalizability. So as your model gets really, really good at answering X, Y, and Z questions, and it's getting even better at that, it becomes an expert. It loses its ability to be a generalist. So it loses its ability to answer broader, more generalized set of questions. So there's a trade-off there between fine-tuning and generalizability. As you are working with these models and as you're trying to implement them, another piece of useful nomenclature is zero-shot, few-shot, one-shot learning. So when you are designing your prompts, when you are writing in your text to send to your large language model and asking it to do something for you, they do better if you give them examples. And maybe you're designing this in a systematic way. And I'm not talking about when you're using GPT and you're just writing a prompt within like a text-based ChatGPT interface. I'm talking about when you're actually deploying an automated architecture that there's no human, it's just a robot that is collecting information from X place, designing a prompt, adding some context to it, sending that request off to GPT, getting that responsive information back, and then moving it along down a system. So I'm talking about using GPT from an automation perspective. It can be helpful to design multi-shot prompting. So zero shot just means you don't give it any examples. Few shot means you give it a couple, and one shot means you of course just give it one. So that's all that means. Here's an example of few shot examples. Your input, you're saying, hey, this is what I want you to do. Here's a couple of examples. And then this is the type of output. So it's kind of like a 3-part prompt. This is the type of output I might want from you. So here's one example. Great product, 10 out of 10. That review was a positive review. So maybe you're asking your model, hey, I'm going to give you a review, and I want you to tell me if it was a positive review or a negative review. Here's an example of other reviews and what their ratings were. Great product, 10 out of 10, positive. Didn't work very well, negative. Super helpful, well worth it, positive. Okay, here is my input. If this is what I'd like you to tell me, is this a positive or a negative review? It doesn't work. And in this case, it tells you negative. This is, of course, an oversimplified example, but the idea is relevant here, and it broadcasts to more complicated examples. So that's few shot prompting. I meant to put a picture here. Limitations and challenges. There can be limited context windows, but these grow with every single release. It seems that the context window grows. Large language models, of course, don't have as good of memory as we do. They can be challenged to remember very, very long periods of conversation. So if you had a conversation with me last year, I would probably still remember it. If you talk with a large language model every day, it may not remember exactly that conversation from that long ago. So there's some challenges from a memory perspective. And of course, I've touched on bias a couple times, but I can't iterate that heavy enough that there's bias in large language models. And overfitting, as we've seen with many neural networks, are prone to overfitting. So it can overfit to those patterns. And of course, anytime that you put information into GPT, into ChatGPT, or any of these public domains that are not private domains secured by your company, they use that information for retraining of the model. So this is not a limitation or a challenge. This is just a warning and education piece. So large language models are like social media. Whatever you put into those becomes fairly permanent in terms of training. Even if you delete it, you didn't really delete it. So just for your awareness and edification, be careful what you put into those. I would not, for example, put your company's proprietary information. I would not put personal identifiable information or very sensitive information that you don't want to exist on the internet. Putting that in there is essentially adding that to their bucket of information that they use to retrain their model, and could be potentially exposed as output or exposed through some hacking in the future. So there's this whole, what I didn't touch on this entire presentation was this thing called prompt engineering, because I don't know, because I don't know that the emphasis needs to be put here. I think you guys are data scientists and experts in the model mechanisms itself, and this seems sort of like an afterthought to me, but I thought I should mention it just so you're aware of it. It's just the way that you design that prompt. So 0 shot, 1 shot, multi-shot prompting can be part of your prompt engineering. Here's a particular example that runs off the page because it's too long, but this might be a prompt. Here's my style between these brackets. The style is how you write in sound. This is not what you should write. This is how you should write. Here's a style. and here's the ban list of words. Somebody had posted this on LinkedIn, by the way. I should have given them credit up here. So this is like a way of creating and engineering a prompt to get a very particular response. You can see you will be penalized and fined $1,000 if you use words from this ban list here. And I've used this. It actually works quite well. So this is like quote unquote prompt engineering, designing your prompt in a way that generates your appropriate output. The reason I didn't put as much emphasis on this is because I just think that this field is so new and we haven't had a chance yet to really operationalize a lot of this, that over time, just like everything else, this will just become a package that we leverage and we program into PySpark. And this is already happening and it's gaining momentum. The most substantial one I've seen so far is DSPy. It's DSPY. And it's a package that you can actually use to design your prompts in a very consistent manner, but in a way that allows you to try a variety of different manipulations to your prompt to really see how things are going. And it's what I would recommend if you're actually building or deploying something to production. That's why I didn't put the emphasis on prompt engineering, because it's just not scalable to have one human design your prompt the right way every single time. We are statisticians and data scientists, so we want really like concrete, reproducible ways of designing things. We're just at an immature part in the field. And so this is evolving. So DSPy, I would recommend looking into that. I've found it to be a very useful package in many ways. You'll also hear something called context. The context of large language models. And I love this word because I think it is very, it just resonates soundly with the way that we think of context when we're talking about conversation. So if somebody says something, well, did you hear that so-and-so said XYZ? Your first question might be, well, what was the context? What context were they saying that in? What was the situation? Did you hear them say that it was a terrible day today? Well, what was the context that they said that in? What were they referring to? And this is really the way that large language models work as well. So when they answer your question, when they provide you a response back, they're providing it in context to something. So what was the context that you provided the language model? What was the text or the prompt that you provided it? What was the information that it was retrieving from its system in order to provide that response? One of the first implementations, early implementations of these large language models was when in the enterprise setting, when people went to implement proprietary implementations, was something called a RAG architecture, Retrieval Augmented Generative Architecture. And the reason this became popular is because everybody didn't want the large language models to be able to expose all of their knowledge and information to employees. So if you're an employee chatbot, you're an internal chatbot, you don't want your chatbot to opine on the distance to the moon. You don't want your chatbot to opine on a Ferrari car. If somebody asks something like that to your chatbot in an internal employee in an enterprise setting, you probably just want it to say, hey, I'm not really an expert in that area. I can't provide a response for you. Can you ask me a question along these lines? This is where my knowledge is. And one way of doing that is implementing this thing called a RAG architecture, where you, as a human, we generate the query, and instead of just taking this query and wrapping it in our prompt, sending it straight to the LLM and generating output, that would be the typical way of doing it. Query, prompt generation, LLM output. We're going to take this query and we're actually going to embed this query. And so if you are asking what I work for a remote company, and maybe I'm asking, can I take my computer outside of the country? And perhaps that's some information that exists in something called a policy document that we have, a corporate policy document. And so you're taking this query, my query, can I work from outside of the country? We're embedding that. When we're embedding that, remember that means that we're representing it as a numerical representation. We're taking that textual representation, we're representing it as a vector, and then we're taking that embedded information, and we're going to see how close is that embedding to our documents. So to all the documents that we have, all the documents on policy that we have, which one is closest from a numerical representation standpoint? What's the cosine similarity of our query embedding, our query vector to our documents, our document vectors? And I skipped through some of the pieces in this picture, sorry. We take all of our documents in order to do that comparison. We take all of our documents, we pass them through an embedding model, and we embed them in something called a vector store. So they're already numerically represented, and we're not trying to recreate those numerical representations on every fly, every time we're asking the query. So they already exist as numbers, as numerical vectors in our vector store. And so we're taking this query, we're converting your query on the fly to a vector, and then we're comparing what's the closest vector to our query, that, or what are the closest 3 vectors to our query. Then we're taking that document, those 3 documents that we found, or segments of documents. Sometimes they're not a whole document. Sometimes you do chunking and you store your document a paragraph at a time. So let's say we take the 3 closest paragraphs. Then we're going to pass those 3 closest paragraphs to our query prompt. And we're going to say, hey, here's the question that was asked. Answer this question, but only in context of this information. We're going to pass that to the LLM, and then that's how we generate the output. So when the LLM generates that output, it can't opine on anything else. It's only in context to what we're giving it from our data store. We're restricting it. So essentially, the model only knows about internal information. And if you ask it anything else, it will simply respond it doesn't know. So the only thing it's knowledgeable about are these documents that you've given it. And this is what a retrieval augmented generation architecture is.
I have an example of that in Python code on local models too, for extra credit if you ever want to.
Would you share that? That would be great.
Yeah.
Hey, that's fantastic. Look at that. Bonus credit for you guys. You get another piece of information. That's fantastic. Anything to add to that, Skylar?
Nope. That I don't know. You hit it on the head there with everything as far as the process. Without having it explained and having to fuddle through it myself, it took a lot longer to figure out how to do it. But yeah, no.
Oh, that's impressive.
Well said. Well done.
That's very impressive. How cool. I'm looking forward to seeing that. You know, are we 3 minutes over?
No, we're 1 minute.
Oh, we're 1 minute. Okay, perfect. I think this is my last slide. We won't talk very in depth about this because I would actually prefer to whiteboard this, and I don't have a good whiteboarding functionality here. So we can talk about this next time, or really we'll just tack this on the end of the metrics class. But the most natural question that comes about is, okay, how do you evaluate how well these models are doing? So a model predicts a sentence, and the sentence is the cat jumped over the pond. And that's what it predicted, but the real sentence was the dog jumped over the pond. And is the cat jumped over the pond more correct, or is the dog jumped over the river more correct? That can be a really hard thing for us as humans to decide. If the real sentence is the dog jumped over the pond, is it the cat jumped over the pond or the dog jumped over the river. Is the word being wrong in the middle or at the end better? And so there are academic professionals out there that have come up with really clever metrics for us to actually evaluate and quantify the performance of these models. One of the most transformative metrics in the field thus far has been the BLEU metric, BLEU, and this is n-gram-based metric. And now you guys know what an n-gram is, so you can kind of start to build your conception and understanding of this metric. But it penalizes, it adds a brevity penalty for things that are too short. And some of that is the reason why originally in the beginning, when ChatGPT first came out, its responses were incredibly lengthy. If you guys remember, it would opine forever on something and you'd have to say, give it to me in 2 sentences because it was just so long. And that's because of the metrics and the way that we penalize some of these models. And there is a penalty for brevity. And so we can, I would love to whiteboard GLEU for you, GLEU, the GLEU metric, which I think is gaining even more popularity. I think it's a great metric. I use this in enterprise settings all the time. And so we can chat about that next time, but I know we are at time today. I'm going to pause the recording and then ask if there's any questions.